ABC and triangle XZW, the measure of angle A is equal to the measure of angle X, and the measure of angle B is equal to the measure of angle Z. What can we conclude about C and W? We conclude they are the same. That would be third angles theorem. Okay, now let's solve. 9 times x is 9x. $18 times 54 is 972. Divided by 9 is 108. And triangle ABC is similar to DEF. They want us to find X. So AC is 12, DF is 15. These ratios are going to need to be the same if they're similar. Okay. Well, I can actually see, I can cross multiply. That's actually what I'm going to do. I could look at the ratios, but I love proportions. So I'm going to have 12x, 8 times 15 is 120. So x is equal to 10. So today we're going to talk about how angles affect similarity. We have a little activity we can do. The question, what can you conclude about two triangles if you know two pairs of corresponding angles are congruent? We talked about this in one of the warm-ups. Obviously, you can conclude that the third angle is going to be the same. They actually have you do a little activity here where you draw angle EFG so that E and G are 40 and 50 degrees. Then draw a larger triangle again so that 40 and 50, so that angle R is 40 degrees, angle T is 50 degrees, but that they're not congruent. You can see that this is larger than this. When you actually measure this, then you're going to measure the sides and record the side lengths. They want you to use a metric ruler. What you should end up finding is that the relationship between EF to RS makes the same ratio as FG to ST and as EG to RT, so that you can argue that the triangles are similar. Talking about this in class also, it's another example of why angle, angle, angle is not a congruence postulate, but angle, angle is going to be a similarity postulate. And there is the postulate. We only need to prove two angles because obviously the third angles theorem is going to tell us that the third angle is going to be congruent. So if two angles of one triangle are congruent to two angles of another triangle, then the two angles are similar. So now we're going to determine whether the triangles are similar. If they are, write a similarity statement and explain your reasoning. Here we go. Okay, so determine whether the triangles are similar, and if they are, write a similarity statement, explain your reasoning. Well, I can see that one of the angles is 90 degrees. They have that in common. That's congruent. 64 and 26 add up to 90, so the other two add up to 90. So if this is 26, the third angle here must be 64. The third angle here must be 26. So triangle GKH is similar to triangle D, because angle G is similar to angle D. Then we had angle K, which is 26, so that's CE. Okay, that's how we do that problem. And that walks you through what we just did, if you want to pause and read that. Okay, example 2. Show that the two triangles are similar, ABE and ACD. Well, A is obviously congruent to A. I can see that B is congruent to C. So since two of them are congruent, they are similar through the angle similarity postulate. But also I could tell through third angles theorem that if this is equal, two are equal and this is equal, when I add them all up and subtract from 180, I'm going to get the same remainder. Okay. This angle is going to be congruent to this angle through the vertical angles congruence theorem. These symbols here tell me that these lines are parallel. So RT is a transversal that cuts two parallel lines. This angle R and this angle T are going to be congruent through alternate interior angles. Yes, it could have used these two parallel lines and also said that S and U are congruent by alternate interior angles. I've actually proved that 3 angles are congruent. I only need to prove 2 to show that they are similar. Okay, so you can go through these. Show that the statements are similar, write a similarity statement. Well, if all 3 angles here are congruent to each other, it must be an equilateral triangle, so they must all be 60 degrees. And so for RSQ, these are equilateral triangles, all of them must be 60 degrees. So I can prove that each of these is 60 degrees, I can prove that each of these are 60 degrees, and I can prove that they are all, therefore, similar to each other, okay? And that's basically, you can read what we just said. Okay, for this problem, show that the figures are similar. Okay, so they want to talk about C, D, F, and D, E, F. When you first look at these, you may not even think they look similar. But these are both 90 degrees. Okay, and then the other 2 angles are going to have to add up to 90 degrees. And we can see that if this is 32, this must be 58. And this must be 58. So our similarity here, triangle F, D, E, is going to be similar to angle F is similar to angle F. Okay, and I miswrote that now I see in the purple there. Sorry about that, that's 32. So F, then D, which is 58, D, F, D, E is 32 degrees here. That's going to be similar with C, which is also 32 degrees. And E, in this triangle, 58 degrees, is going to be similar to D in this triangle. And if you need it written out, you can do that. So problem number 3, they ask us, suppose in example 2, the 2 lines, SR and TU, were not parallel. Could the triangles still be similar? So let's go back and look at this problem. This is the problem that they were talking about. Okay? If these 2 lines were not parallel, if you remember, we talked about SU being congruent or TR being congruent. If these lines are not parallel, then obviously SU or TR are not congruent. But we could have a situation set up where either S and T were congruent or R and U are congruent. While we can't tell from this drawing, it is still possible that the triangles would be congruent, even though with the information that we have right now, we cannot actually prove that. Okay, now we're going to apply some of what we've learned in what's called indirect measurement. And where you're going to use measurements of buildings and different things using similar triangles. So this is an example of how this would work. This is a standardized test practice, where basically we have a flagpole that's casting a shadow that is 50 feet long. And at the same time, a woman standing nearby who is 5 feet 4 inches is casting a shadow that is 40 inches long. Because basically the sun is so far away that as the sunlight hits the top of the woman, she creates a shadow, and the sunlight hits the top of the flagpole, creates a shadow. Obviously, for this to work, they need to be standing next to each other at the same time of the day. If the woman's standing at 8 a.m. and you measure, and then the flagpole at noon, the sun's going to have shifted. But at the same time of the day, this works. Now you'll notice that these numbers are different. This is 50 feet. And here we're talking about 40 inches, and 5 feet 4 inches tall is 64 inches tall. So I want to convert this 50 feet to inches so that everything works. Actually, you know what? This is going to work without even converting it. So 64 inches over 40 feet, or over 40 inches, excuse me, is going to be equivalent to some number over 50 feet. This number is going to be in feet. So 40x equals 64 times 50, 3,200. Divide both sides by 40, and you get 80. The flagpole is 80 feet tall. If you need it again, here is a drawing that they've made of the triangles and have walked through setting this up. They did set up the proportion differently because they're comparing the height of the shadow and the ratio between the shadow length, and the shadow length of the woman. This will work also. You get the same answer. I set up my proportion differently. Same type of problem here. If a child is 58 inches tall and she's standing next to the woman who we had was 64 inches tall, and the woman's shadow was 40 inches, how long is this shadow? So once again, I'm going to do x over 40, and that's equal to 58 over 64. So over here we have the ratio of the length of the child's shadow to the length of the woman's shadow. Over here we have the ratio of the height of the child to the height of the woman. 64x 40 times 58 equals 2,320. Divide both sides by 64. And you get the child's shadow is just a little bit more than 3 feet, 36 1/4 inches. And one more guided practice. You are standing in your backyard and you measure the lengths of the shadows cast by both you and a tree. So this is you, and here is a tree. Since we live in Florida, I'm going to make it a palm tree. Write a proportion showing how you can find the height of the tree. So you can find, there's many ways you can do this. You can do the ratio of your shadow to yourself and compare that with the tree shadow and then the tree's height would be x on the bottom. You could do your height to x over x, the tree's height, the height of your shadow, over the length of your shadow, or the length of the tree's shadow. I give you their sample answer. So there's a few different ways you can do this. So determine if the two triangles are similar. If they are, write a similarity statement. Okay, so triangle ABE is going to be similar to triangle, well, A is going to be the same as A in both triangles. E and D are going to be the same. So through angle-angle similarity, they must be the same. That means that B and C are going to be the same, they're going to be congruent. The angle-angle similarity postulate tells us that they will be similar. And there's the similarity statement. For problem number 2, this angle is going to be similar to this angle. The other two angles, though, in P and M are 7 degrees and 55. Since these are not going to be similar. Okay, find the length of BC. I know that these two angles are going to be similar because these two are going to be the same. They're vertical. Since these two lines are parallel, we're going to have alternate interior angles cut by transversal AD. So they're going to be similar, so I can use a proportion. X to 5. Okay, so this side is going to be similar to this side. Let's write this out. So triangle ABC is going to be similar to triangle A is going to be similar to D. That means that B is going to be similar to E. So here if I have side BC, BC is similar to EC, which is 12, and AC is going to be similar to CD or DC, which is 8. So 8x equals 60. So 60 divided by 8 is going to be 7.5. Problem 4, a tree casts a shadow. It's the tree, that's the shadow, is 30 feet long. At the same time, a person standing nearby who is 5 feet 2 inches tall, so that's 62 inches tall, casts a shadow that is 50 inches long. So I'm going to set that up. You can set this up a number of different ways, 62 over 50. Since I have over here the height of the person, I'm going to put x, the height of the tree, over 30. So 50x equals 62 times 30, which is 1,860, divided by 50 is 37.2. So rounded to the nearest foot is 37 feet. Okay, and then you can look through